Hello, everyone. I am Riqiang Wang. I'm presenting the double decoder improving latency for streaming end-to-end ASR models. This is work by DIALPAD ASR team here in Canada. So let me first talk about what this is about. So at DIALPAD, the application that we have is that we have a lot of people making phone calls through our system and also video calls through our system, and they would like to get real-time feedback or real-time insights from these calls. And how we do that is we first transcribe the audio of the calls to speech to text, and then we have a bunch of other NLP models working on the text, and that would provide some insights to the speakers. So because of that, while all the others have been focusing, a lot of other work have been focusing on larger models, such as the Whisper. Our goal is to get better latency while maintaining or improving the word error rate. Here we present a solution that we came up with, which is a new decoding algorithm that we call the double decoder. This is a very simple technique, and we're surprised that we haven't found anyone else presenting it anywhere. So we would like to share it. Specifically, when we're looking at previous work, there was a lot of focus on encoder improvements. For example, there's the cascaded encoders. And for all these encoder improvements, the thing is that we need to retrain the models. By using two models, as in the cascaded encoders, you also increase a lot of the compute for running two encoders in parallel. And also a lot of work focuses on RNT models, whereas we feel that CTC models have been neglected, and CTC models can have advantage in a streaming scenario where they typically have a lower real-time factor while we're decoding. So let me present this simple decoding technique. But first, let me also talk about a little bit how it is usually done. So for streaming audio, ASR or speech recognition, the default is that the stream comes in chunks, and then we pass in each chunk into the ASR model that we have, and which we call the default decoding. And then we here denote external decoder, which combines the output, or rather updates the output of the model at each time step to provide the hypothesis text. And here the external decoder means that it could be greedy decoding, which is just the argmax of the log probability output of the model, or it could be a beam search decoding with the external LM or something else. And here I also note a darker area at the left of xt+1, which is kind of a optional history, which for RNT models, for example, it is inherently included in the model because incorporates the context from the history. And then we have known for a while that by having more context, we can basically increase the accuracy and improve the word error rate in the middle chunk of longer chunk of audio. So a naive improvement of the default decoding is to add a right-hand side look ahead. Here, basically, so we wait for the duration of LT, so that we have a little bit of audio there, and then we output we concatenate that with the XT and history. And then we output only the model output of XT. So basically, we're waiting for the LT to accumulate, but using that as a look ahead or context for XT, but then discarding it at the decoder time, which causes a huge delay, even though it increases accuracy. And the delay is constant, the duration of LT. So our proposed method, which we call the double decoder, is very simple because we basically add a temporary decoder, which also decodes the content of the lookahead, and then instead of discarding it, we output it as a temporary hypothesis. And at the next time step, for example, this hypothesis is discarded, and then only the output of the external decoder here, which represents the output of the center area XT of an audio chunk, is concatenated to the history to become the final text hypothesis. So by using this method, actually the result is pretty deterministic. And so the latency decrease, as we can see from the graphs before, it is basically the duration of LT, because we don't need to wait for LT to decode XT. And then we would expect a little bit of increase in the decoding time of the look ahead. So we minus that. And then, so we basically need to prove that the decoding time is not greater than the duration of LT for this to be beneficial. And the word array would not change if we consider the output from the buffer decoding and double decoder, because only the same area is used for the final hypothesis. The only thing we note that might be a downside is the reduced stability, because that we will discuss later. And then we did experiments on the Conformer-CTC model from NVIDIA, as well as the Zipformer-CTC-Transducer model from IceFall Toolkit. And these are pre-trained models trained on LibriSpeech, and one is 13 million parameters, one is 66, relatively small models. And we decode these on the Cascade Lake CPUs. So I just want to quickly show the results here, where basically because the improvements are mainly deterministic, we want to study the effect of context size and the latency and the look ahead and their relationships. So here we can see that the write context, the look ahead increases, but the decoding time of the write context of the look ahead actually slightly decrease. Yeah, basically we achieve the same amount of latency improvement from the duration of the write context. And by increasing context, of course, we achieve better word array compared to the default decoding. And for the Zipformer as well, we wanted to show that, especially compared to the default decoding, using the same context size, and then if we sacrifice some part of that audio chunk as the look ahead, we improve the word error rate, as well as improving the latency. Well, in this case, the latency wouldn't change. In terms of the stability, I just wanted to show an example here where you can see that for buffered hypothesis is on the left, and then double decoder on the right, and the y-axis is going down, is increasing in time. So the double decoder outputs immediately, whereas the buffer decoder is still lagging. The only thing is that sometimes double decoder will output wrong words, for example, in the second line, and also in the second to last line, where it would be corrected when the final hypothesis is produced. And we find an interesting phenomenon that where in the LibriSpeech test other, the stability is worse than in the test set, the test clean of the LibriSpeech. So there's more work to be done for real life scenarios in terms of noisy speech, and if we want to minimize the negative effect of this method. So to conclude, I wanted to introduce this very simple reuse of the look-ahead chunk of the audio when we do speech recognition. And we think this brings a better balance between word array and latency. And for future work, we aim to work on the stability improvements and also hope this method can be implemented in more applications. Thank you.